This is tutorial number 5, and we're going to be discussing frequency and wavelength for the Foundation Theory course. The voltage that comes from batteries is direct current because the positive and negative terminal of the battery is always positive and negative. Suppose we had a voltage that started 0 volts, and that voltage was one polarity, and the voltage rose to, say, 10 volts, and then the voltage falls again back to 0. Then the voltage changes polarity and rises to 10 volts with the opposite polarity. That voltage is called AC, alternating voltage, because the voltage is continuously climbing to 10 volts with one polarity, falling to 0, climbing to 10 volts with the opposite polarity, and falling back to 0. If we were to plot a voltage like this, rising and falling, up and down, up to 10, changing polarity, up to 10 again, back to 0, up to 10. If we were to plot a voltage like that against time, we would get something called a sine wave. And sine waves are very important in radio and electronics. And you can do it yourself. All you've got to do is get a pencil and paper and move your pencil up and down as quickly as you can, and then without changing the up and down motion, move your pencil to the right, and there you go. That's a sine wave. This is 10 volts here. I didn't go right up to 10 volts. This is 10 volts. This is 0 volts in the middle. So here is 1/2 cycle of the sine wave, rising to 10 volts and falling to 0 volts. Then the polarity changes, voltage rises to 10 volts and falls to 0 volts. All radio signals and AC signals are the same thing. The only thing that changes is the number of cycles per second. Since this is time, this is seconds. And how many of these cycles, that's one cycle there, how many cycles per second is the frequency? So the next cycle is here. So we've got just over 2 cycles shown on this slide. So how many cycles per second is the frequency? And the unit of frequency is the hertz. And the other thing that's important to us about sine waves is the distance between here and here. The distance that one cycle travels is called the wavelength. That's the distance from there to there. I'll show you on a better slide shortly, is the wavelength, and the symbol for wavelength is the Greek letter lambda. Let's have a look at a little bit better diagram. Here we've got a better sine wave. Let's have a look at it. This is 0 volts here. This time, the time taken for one cycle, and that is one cycle between there and there, is called the period, and the symbol for period is a P. And the number of cycles per second is called the frequency, and frequency is measured in hertz. The two things you need to know about for sine waves is their frequency is the number of cycles per second, but see how many cycles we've got here. That's one cycle. That's 2 cycles. That's 3 cycles. So we've got 3 cycles here. If the time from here to here was 1 second, we would have 3 hertz. 3 cycles per second would be 3 hertz. You need to be able to convert frequency. If you're given frequency, you need to be able to find this distance here, which is called the wavelength. And the symbol for wavelength is the Greek letter lambda. Now you need to be able to convert, given the frequency of a sine wave, you need to find the wavelength, and given the wavelength of a sine wave, you need to find the frequency. And you can do that mathematically, but in your foundation exam, you'll be using a nomograph, a table, to do that, and I'll show that to you shortly. Sine waves are produced by AC generators. The power station that delivers the power to your home is an AC generator, and it produces a sine wave of voltage like this. So this is what the voltage looks like at the power point in your home, except this comes up to around about 339 volts there in your home. You don't need to know that. You do not have to remember anything about this slide at all, but I just wanted to show you how AC is produced in a power station. For some learners, it all sounds a little bit complicated, that as voltages in a power station or radio transmitter can produce sine waves, the waves shape that we were just looking at. This is how power is generated in a power station. A magnet is moved in and out of a coil of wire, and by Faraday's law of induction, you don't have to remember this. What I wanted you to see is just the coil of wire, the magnet moving in and out, but in particular I wanted you to notice what's happening to the voltage that's being produced. As the magnet moves in and out, a voltage is created across this coil. Now look what the voltmeter is doing. The voltmeter is 0 in the center. I'll see if I can enlarge this a bit. The voltmeter is 0 in the center, 20 volts there and 20 volts there. So the voltage is going from 0 to 20, falling back to 0, going up to 20, back to 0, up to 20. That is AC voltage, and that is a sine wave. And the frequency of a sine wave can go from a few hertz to thousands of gigahertz if we wanted. All sine waves are the same, whether they're produced at voice frequencies 0 to 3000 hertz, or whether they're produced at power frequencies 50 or 60 hertz, or whether they're produced at radio frequencies. A sine wave is a sine wave. It's just the frequency that is different. It's important for radio amateurs to be able to convert frequency, and particularly radio frequencies, to wavelength, because this is how they decide or work out the size or length of their antenna. Have a look at this chart, because you do need to know how to use a frequency to wavelength chart for your assessment. You won't have to do any mathematical calculations. You'll be given a wavelength and you might have to find frequency, or you'll be given frequency and you might have to find wavelength. Notice that on the left hand side we have frequency, that's the y-axis, we have frequency in megahertz, and on the horizontal axis we have wavelength in meters. Suppose we wanted to, and you only have to do this approximately for your assessment. Suppose we wanted to know the wavelength of about 144 to 148 megahertz. That's going to be about here. So we want to know the wavelength of 144 to 148 megahertz. So there's 100, there's 200. So 149 is about here somewhere. All we do is draw a line across till we hit the red line. When we hit the red line, we draw a line down and we read off the wavelength. So 144 to 148 megahertz is the 2 meter band, or has a wavelength of 2 meters. Let's do another one. Let's find the wavelength of 300 megahertz. 300 megahertz, go across to the red line, then come vertically straight down, and 200 megahertz has a wavelength of 1 meter. Suppose we had a wavelength of 20 meters and we wanted to know the frequency. 20 meters, follow it up to the line, hit the line, Move left till we get to there, and it's around about 14 megahertz. So 20 meters is about 14 megahertz. You will most likely have to use this chart in your foundation theory assessment. And so make sure that you can convert from one to the other, frequency to wavelength. Be very careful about wavelength. You may be given a half wavelength. Let's say you're told that a half wave dipole is 1 meter long. So if a half wave dipole is 1 meter long, it's a half wave length antenna, so the wavelength is 2. So a 1 meter long antenna has a half wave antenna has a wavelength of 2 because it's a half wave antenna. So that would be on 144 megahertz. Make sure you're familiar with this chart. It'll help you greatly during your assessment. Again, this is a curiosity because you don't need to do this mathematically. You'll be using a graph just like this in your assessment. But if you want to know the relationship between frequency and wavelength, it's not a difficult one. The numbers on this side are the frequency in megahertz. The numbers on the x-axis is the wavelength in meters, and the relationship between frequency and wavelength is simply wavelength. That's this scale here. That's wavelength. This is frequency here. So wavelength equals 300 divided by frequency in megahertz. Very useful equation to remember if you're interested in building antennas. So that's the relationship between those two sides. You can actually use that equation if you want to, or you can just, and it's probably safer to rely on using the chart in your assessment. When we have sine waves or radio waves at very high frequencies, we tend to group them into bands. And you just need to have an awareness of those bands. You don't need to commit these to memory, I believe, or you'll be able to test yourself with the self-testing drill software that comes with the DVD version of this course. But I don't believe you have to commit these to memory, because during your assessment you'll probably be given a table and ask questions from the table. But what I'm going to do is just type up for you the 4 major frequency bands. There are others, but these are the 4 major ones. This 300 kilohertz to 3 megahertz is commonly referred to as the medium frequency band, or simply the MF band. Then we've got 3 megahertz to 30 megahertz. You probably know this one, don't you? That's high frequency, and that's referred to as the HF band. Then we've got 30 megahertz. You see the system here by now, can't you? To 300 megahertz. And that's called the very high frequency, or VHF band. And lastly, 300 megahertz to 3000 megahertz is ultra high frequency, or UHF. There you go. I don't think you have to commit those to memory, just be aware of them. I think if you're asked a question in the assessment, you'll probably be shown the table as part of the question. There are frequency bands other than that, but you're not concerned about them. And quite frankly, most radio amateurs spend all of their time in a amateur band, which is a sub-band of these bands on this slide. Well, that's it for this tutorial on sine wave, on frequency, sine wave and wavelength. I'll see you back with the next tutorial. Please test yourself with the self-testing software. Cheers for now. This is Ron, aka 2D Kid.